So here is my PCB. It includes maybe a microcontroller. And inside that microcontroller there may be some registers. I want to see what is there inside that register. So what I will do is I will take this TDI, go through the boundary scan cells, and then bypass there may be another thing here, bypass, then come back. So I can observe this register, the contents of that register. So you may have used when you develop embedded systems, you may use these kind of boards, right? Maybe you used some development boards. For example, MSP 430 Launchpad. Or some other Raspberry Pi and things like that. Okay. So the PC it runs a software and in that software maybe we want to sort of look at all the registers that are there in that particular processor MSP 430 R1, R2, and we want to show its content. So how is it happening? There is this is our PCB, and through the TDI TDO you can go and fetch the value of this register and you can display it here. So this is sometimes called as emulation. In-circuit emulation. In-circuit emulation. So from a user's perspective, it appears that he is debugging the software. The software is running in this microcontroller, Raspberry Pi or MSP 430, etc. And as a result, registers are changing. And the user may want to see whether the algorithm is correct, whether R2 has got the correct value or something like that. So the JTAG is helping in accessing whatever is in R2 and bringing it back to the PC, and the PC displays the value on the screen. So it appears to the programmer that he has full access to R2. He can fully observe R2 and he can fully control R1, etc., etc. So the JTAG can also be used for debugging. In fact, that has become a very important application of JTAG now. It was originally developed for test purposes. Now let us talk a little bit about interconnect testing, how it is done, right? Now let us say there are two chips. So this is U1 is one chip and U2 is another chip. Net 1, net 2, net 3, net 4 are connections running between the two chips. Okay. So maybe this particular pin is an input to the, okay, this is an input. So this is normally the direct path. These are the functional paths. During testing, what we are going to do is, we are going to start loading patterns like this. See, let us say we load, as he has shown, 1 0 0 0. And we capture it here. So what could happen is, it will capture 1 1 1 1. The reason being, there is an open circuit here. So this 0 may not travel here. I am sorry, this is my mistake. It may capture 1 0 0 1. Okay. So this 1 came here, this 0 came here, this 0 came here, but we are not able to get this 0 here. We are capturing a 1. So that gives us a clue that there is something wrong. Then we may apply 0 1 0 0. That 0 comes here, and unfortunately a 0 is coming here also, because there is a short circuit between these two guys. So that 0, it should have been a 1 here, but a 0 is here. So this short circuit is causing a 0 to get trapped. So that is how interconnects are tested. Okay. So we try to see whether a 1 can go correctly from here to here and a 0 can go correctly from here to here. So if we can guarantee that each wire can take both a 1 and a 0 correctly and transport it, then that means the interconnect is okay. So interconnect testing. So imagine that I have some 8 wires. So we can apply these patterns 0 1 0 1 0 1 0 1, then 0 0 1 1 0 0 1 1, then 0 0 0 1 1 1 1. See, now what has happened is, if there is a short between these two guys, we will be able to detect, right? We will be able to detect it here. So initially, let us say we, in this resistors that are here, we want to transport a 0. So, before we transport, we can put a 1 here. So, let us say we put all ones. Or let us say we put 1010. We can scan in 1010, 1010. Then we scan in 0101 this pattern into the boundary scan cells. And then we do a capture. So, if all goes well, this 0 should come here, but if a 1 still remains, that means there may be an open here. Similarly, if a short is there between these two, it may cause this 0 to be a 1 or a 1 to be a 0. Okay. So, that is how you can test the interconnect. You can bring a 0101 pattern, then the 0011 pattern and all 1 pattern. So, that sort of makes sure that we have placed opposite values between every pair. So, let us say we call these wires A, B, C, D, E, F, G, H. See, the very first pattern has exercised opposite values to A, B, C, D, E, F and G, H. They have placed opposite values. In the second pattern, we are taking care of B, C, and maybe we have taken care of E, F, isn't it? No, this one, what is it? A, B, C, D, E, D, E, and A, B, C, D, E, F, J, F, G. And in the next pattern, we have taken care of this guy. A, B, C, D, E. So, we have managed to sort of see, we may not be so keen to see whether these two get shorted, that is very unlikely. So, the near ones that can get shorted are A, B, B, C, C, D, then D, E, E, F, F, G, G, H. So, we have sort of managed to get all those combinations. And we should try and get both 0, 1 and 1, 0. So, in the first one we have managed to get 0, 1. Here we have managed to get 0, 1. Here we have managed to get 0, 1, 0, 1, 0, 1. You can invert all the patterns. You can also make these patterns. So, this will be even better if I am willing to put all these patterns and test the wires. Then I have tested every near neighbor pair, with both 0, 1 and 1, 0. As a matter of fact, this pattern, the first pattern, is also in a way exercising A and C, if there is a short between A and C. It will also exercise if there is a short between A and D, and so on. So this is how you perform interconnect testing. So using this JTAG standard, you can get full test access to any one of the chips and perform the tests that you have derived, either digital tests or memory tests, and then apply those tests. Plus you can also test the interconnects. So in a way, it helps you to test the entire system, and it helps to debug the system also. Okay, we have talked about that. So that is the advantage of this JTAG standard. More recently, they have also developed JTAG, or rather interconnect standard for analog test. Okay, so let me show you that also. So analog test bus. So that is the 1149.4. 1149.1 is JTAG, whereas 1149.4 is the analog test bus. So we may even have a picture of this. Okay. So you can see that it allows you. I think there are only two wires, AB1 and AB2. Okay. Using that, you can go ahead and get analog access to any one of the internal lines. That is basically the idea. So you may find Professor Vishwani Agarwal's slides also. So please go through that also. So the analog JTAG test capability, it's oriented towards measuring external component values or internal impedances, not intended for DSP type of analog tests. Okay, simple tests. It's usable with digital JTAG boundary scan, adds analog testability, both controllability and observability, eliminates large area needed for analog test points. There may be some measurement error, that is the cons, and so I think this is you can use this to understand. So normally TDI, TDO, TCK and TMS are part of the digital testing, but here they have added 81 and 82. And these wires can go and directly access the analog modules. Okay. So that is the advantage of the analog test standard. Okay. So it's something that you can read up. Okay, you can read up. They have also described how if there are multiple chips on the board, then how to connect 81 and 82. So people who develop these ICs, they must stick to the standard. They must provide TDI, TCK, TMS and TDO. Okay, then only it will be compatible. Similarly, if you are going to stick to the standard analog test bus standard, you must provide those 81 and 82. That's an overhead. Okay, these extra pins will have to be supported by you. But today, I think all vendors, they have universally accepted JTAG, and they provide this TDI, TDO, TCK and TMS. So, as a result, you can sort of, there is some interoperability. Okay. So, early days they used to use this ad hoc test methods, and there was no standard like JTAG, and people will not provide TDI, TCK, TMS, etc. But today the overhead of JTAG is obvious, right? You have to have extra area for these boundary scan cells. There is some extra connectivity, power. Yes, all these are true. But look at how simple it becomes to start testing your chip. So that is a great advantage. So people don't complain about the area overhead, power, or performance overhead, etc. Okay. Similarly, it's a great way to debug. All right.